Welcome to the shop where I'm overcomplicating a project today for your benefit. I've got to make a lawnmower bracket today, and this bracket goes kind of on the front of the mower and controls the deck height. Seems that we've had a little damage to the mower and we've got to fix it today. And I could have made this a couple of different ways, right? I could have taken this bar, I could have heated it up here, I could have bent it around and kind of dealt with whatever radius I'm able to achieve on the limited equipment behind me here. I could have done a MIG weld. I could have done a stick weld, right? This is carbon steel, but I thought I would TIG weld it using the Lincoln Square Wave 205 for a couple of reasons. One, I like to TIG weld, no sparks, no spatter, no slag, not a lot of smoke in the shop, so that's a good thing. I can wear this light knitted shirt, right? It's a arc rated shirt and not have to worry about putting on too heavy a gear to protect myself from sparks. So that's a benefit too, because it's a hot, sticky mess in the shop today because we're in the middle of that Midwest heat wave. Here's that Lincoln Square Wave 205. I've had this thing for just under a year. It's been performing rock solid. I'm running on 230 volt primary here today, and we've got DC TIG mode set up. The pulsar is off and our post flow is on auto. So if I just hit the back button, we're right back at the main screen. I'm using the remote foot pedal here, and that foot pedal is giving me remote amperage control while I'm welding. So that's the benefit of TIG, is controlling your current on the fly. And if you want to go faster, just keep adding heat. So what I'm going to go ahead and do is I'm going to show you what I did. And probably the biggest thing is the prep. This is a hot rolled steel, something that you can pick up at any hardware big box store. I got it dropped off and it was left over after another project. But hot rolled steel means that as this was made, it was allowed to slow cool in air from the red hot condition, right? So what we end up with is a very heavy mill scale. And while flux core and arguably stick and maybe even a little bit of MIG can tolerate some of that mill scale, it's always best to start with clean material. And with TIG welding of carbon steel, that's super important because this outer coating, this nasty, trashy material, right, that's left over from the manufacturing process at the mill, is gonna hold on to moisture, contamination, oils, and all kinds of crud that could contaminate your weld. Flux core and stick welding have enough deoxidizers and slag formers that they float those impurities to the top so that it doesn't end up in your final weld. With TIG welding, we don't have that type of flux and slag formation that's going to help us clean. So TIG is way more susceptible to surface contaminations. And yeah, I could weld this without cleaning it, but my tungsten's going to get boogered up on the end as things are burning off the material. My weld could have porosity in it, and it's going to smoke a heck of a lot more because what I'm doing is I'm burning the mill scale away. So what I did is I hit it with a flapper disc. I cleaned up the edge of the material where I'm going to weld. I cleaned up the end of the material, and I cleaned up the back side of the material just to start with good practice, right? Then I have my other part here that I'm going to go ahead and weld on. Now, I'd like these to be as close to 90 degrees as possible. And I say close because it's kind of like horseshoes. This is something that we're working on. It goes out in the yard. So it doesn't need to be perfect. But I do want to make it look presentable. So here's what I'm going to do. I'm going to use this piece of angle here to create my corner joint. And that's going to help me maintain alignment while I tack it and while I put a weld on. Then I can flip it over and do it on the other side. Getting a 90-degree angle when you're welding something is somewhat difficult, especially when you're first starting out, because we're going to be dealing with distortion where the weld is shrinking about 10% of its average width. So that's going to pull. We're doing an outside corner, so actually that might help us maintain some of that alignment. And distortion's not just going to all pull it one way. If we were to do, say, an internal fillet weld right here, that thing is going to turn whoop, just like that. What we're going to do is try to set this as an open outside corner here, just like that, and I'm going to fill that in. It's going to look kind of like a groove weld, more like a groove than a fillet. Okay, so as we get in there, it's going to have a tendency to pull in a different way, pull in a different direction. If we keep it clamped up, it's going to minimize that distortion that we get. Okay, and this is also aluminum. Aluminum, one, will not weld the steel. It takes a lot more current to get a puddle going, so I'm not real worried about sucking that aluminum into the backside of my weld. It's also going to serve as a heat sink because aluminum is a lot better conductor of heat and electricity than plain old carbon steel. So as I'm welding this, that aluminum backer is going to continue to suck the heat away. However, just be careful because aluminum heats up pretty quick. So if I'm welding down here, this aluminum could be hot on the other end of the piece, right? So at the end of the day, that's what I'm going to tackle. I'm going to use some of these handy dandy clamps, and we'll see if I can get this fumbled in approximately the right orientation. All right, I'll leave just a little bit of a gap. Some angle iron or angle material will have a slightly radius edged, and that can be a benefit as well, because it's gonna give us a little gap behind the root. So if we're getting full penetration on the joint, it gives you somewhere for that weld to go, right? And by putting a backer on there, we're also using a form of shielding, because we're not allowing any air to get to the backside of the weld, which is going to make it look kind of nasty. So in this case, with having that backing bar, it's going to hold the argon in the joint, and we're not going to have that same level of contamination that we would get if we were trying to just do this open. All right. Okay, so here's what I got. I got my piece cleaned up on both sides, looking pretty good. I'm going to put it right there in this orientation, and then we're going to take this other clamp here, and arguably, right, they probably make clamps like this that you can go out and buy. In fact, I know they do, right? Like a picture frame type of a clamp. Maybe you're using a fireball table or one of those modular fixturing tables. You may have a lot better way of doing this. I'm using what I have in the shop and kind of improvising along the way to get the best that we can, knowing that we all don't have the perfect setup out there when we're trying to do something like this. And yeah, it's going on the lawnmower, so it doesn't have to be pretty. But if you go over and look at somebody's lawnmower and they call themselves a welder and their welds look like crap, find somebody else to do your work. We're going to end up with a joint that looks something like that. It's an outcut side corner joint. We're not getting any overlap of the material. It gives us full access to the root of the material. And when I put this weld in there, if I can fill that joint in a single pass, we should have pretty much 100% joint penetration. At least that's what I'm hoping for. Just check my final alignment here to make sure we got a straight weld going across. I'm trying to align it on the sides, and I'm trying to align it across the weld here. All right, I like where that is. Now, I'm using mild steel filler rod, which has a copper coating on the outside. The copper coating is there primarily for one reason, and that's to stop it from rusting. It will still develop a little bit of surface corrosion if it's left in a humid environment for a long period of time, but that copper coating really does help a lot. I prefer a low S number, like an ER70S2 wire, because it's got less deoxidizers, and we've already removed a ton of this material, so why do I need that extra silicone of an S6? S6 is typically designed for MIG welding on dirtier material, and that higher number has higher level of deoxidizers. So if we were going to weld on dirtier material and not take the time to clean it, that S6 with that silicon is going to grab onto oxides and different trash in the puddle. It's going to float it up to the surface, and you're going to see it on the weld. Consequently, you will see more of that silicon on the surface if you don't clean your material than if you do. Okay, so cleaning your material helps get rid of the trash. It ensures better success. You can't jump right into the fun part, the welding part. That's actually the easy part, right? The hardest part is the prep, the alignment, and getting ready, making sure your settings are all good, making sure your equipment's good, making sure your argon's on. And in this case, I'm going to be using a foot pedal. I'm sitting at a bench. I'm going to have control. I got a little stool here that I'm sitting on. And at the end of the day, what I've done to my TIG torch is I popped out the remote control and just put in this blank insert, right? Which plugs the hole so I don't get any dust in there while I'm using the torch. And it still lets me use this nice ergo torch and get the maximum benefit out of it. So this thing is super flexible. You can use it with a remote built in, or you can use it with a foot pedal and just put that blank insert in there. Let's PPE up and get going. What do you say? Here's our weld joint all set up and ready to go. We're going to put it right down in that orientation, and I should be able to sneak my TIG torch in here just like that. Boom, 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 make that weld. All right, I welded about half of it just so you can take a look here at what I'm seeing. Nice clean puddle all the way across. It is a little bit gray. One tip you might want to think about is you could add a little bit of stainless filler rod in there, make it look a little prettier. But at the same time, we're going to paint this, and stainless doesn't hold paint very well. So we're going to go ahead and use carbon steel. Now, I didn't fill the whole joint there. I went ahead and put in a little root pass. Then I could go back over and cap it. What I'm going to do from here on out is I'm going to try to fill the whole thing in, carry a little bit bigger puddle so you can see what that looks like. Let's take a peek. As a comparison, here's what we've got. We've got a smaller weld put in first. And we've got a bigger weld where we tried to fill the whole joint. And in this case, the material is thin enough that we could do that and probably get away with it, right? I'm going to fill in this part next, and I'll probably run over the whole thing so it looks like a uniform weld. There we go. We got our finished weld right there. A little bit of finishing, should be perfect. And here's a TIG welding tip. I don't know about you, but I find that having good rhythm gives me a nice ripple pattern across the weld. And I figured that out welding aluminum. When you want your aluminum welds to look good, you've got to have steady dipping rhythm combined with steady motion of the torch so that everything's evenly spaced. And one of the things I find myself doing in my head is counting every dip. Have you ever found yourself doing that? 22 dips, by the way. Now for the moment of truth. Let's take this thing apart. Okay. Put it over here. I'm wearing gloves so that I don't burn my hands. And we've got 100% joint penetration. We've got our weld over there. We didn't blow out the corners because we backed off the foot pedal as we got to the edge and we added just a little bit of rod there. At the end of the day, we could probably touch this up. I got a little bit of joint sag, probably a little bit of underfill. If you can see right there, it's a little low in the middle. I call that underfill, not undercut, because it really needed more wire. It would probably have helped if I'd used a larger diameter filler rod. I was using 1/16 ER70S2. If you jump up to a 332 filler rod, you're going to have to dip less, and you may find that you get a little bit better filling. Just a caution there, though. When you go up with filler metal diameter, especially on steel and stainless, it takes a lot more energy to melt that rod. That's why with these materials, I try to use a 1/16 filler rod. On the other hand, if you switch over to aluminum, aluminum's such a good conductor of heat. I rarely use 1/16 aluminum rod because it melts before it gets to the puddle. So instead, on aluminum, I go up one size filler rod that I normally would use for steel or stainless. That's a tip. It might help you. Let me know what you think. So I'm happy with that. Let's check our squareness. Look at that. Pretty decently square, right? Because of the joint design that we selected, we got a pretty square weld out of that. Probably more square than if I'd have tried to heat and bend it using the tools that I have. So I'm happy with it. We're gonna go ahead and attach the other side. All right, we're gonna do the same thing. Make sure that we got the brackets pointed in the right direction. We don't want to put them on backwards. It's not going to work right. That's probably the only critical thing about this whole assembly here is that we got to do that. Okay, so let's go ahead and tack or clamp our first piece on there. I'm going to say as square as we can get it because close enough is good enough in my book for this job. All right, then we're going to go ahead and put our other piece on here. Just like that. Okay, I think we're ready to go. All right, so here's a picture of that weld. I made this one in a single pass from this side to this side, moving in a right to left direction using a forehand technique. I like to go, just a little bit more than recommended. It gets the tungsten out there so I can see it. And I start to look in this type of a joint for a puddle that looks like a teardrop, right? slightly elongated to the front. I call it a guitar pick. Once you see that guitar pick happening, you know you're ready to just start flying. And if you lose the guitar pick, you've either lost the puddle, you've used too much amperage, or you got the wrong angle. So make sure you pay attention to that. So here's the first side that we did. If you remember, on that first one, I did a root pass about halfway across, and then I capped it over the top. So you can do that if that's the level of your skill, or you can carry a full puddle all the way across, kind of like I did on side B right here, all the way across. And again, we're getting a consistent ripple pattern there because I'm trying to coordinate the timing of my travel speed and the dipping frequency. Every time I dip the rod, it makes a nice ripple in the weld pool. And look at the shiny backside. Again, because we had that clamped up with a fixture, all the penetration that we got through the joint ended up being protected from the atmosphere, and we didn't get any of that nasty oxidation. All right, and here's the root pass on the other side. And if we can trust how square this protractor is, I'd say we did a pretty good job keeping those tabs squared. It's definitely going to fit where the bracket needs to go. Okay, so as a recap here, we used DC TIG, no pulse, and automatic post flow. I was running 100% argon at about 20 cubic feet an hour. We used 1/16 ER70S2 filler rod, which had a copper coating on it to prevent oxidation of the rod between welds. And at the same time, I was using 332 2% ceriated tungsten. Any DC tungsten would work. Cerium works fine. Lanthanum works fine. Of course, you can use the purple tungsten, not the green tungsten, anything but the green tungsten. Unless you're talking about that odd chartreuse color, something about a laser tungsten. Or so that's where we're at. We got this thing going back on the lawnmower. Remember, when you're welding carbon steel, clean it, clean it, clean it, because it's going to be oily, it's going to be greasy, it's going to hold on to oxides that make welding a whole lot more difficult, especially with TIG welding. When you jump over to stainless, stainless doesn't have that same issue, right? It's not absorbing those things into its oxide layer. No, the oxide layer is stainless. It's chromium oxide. So usually people go from welding stainless because it looks the best, and they start TIG welding mild steel, and they're like, wow, that looks like poop. And it kind of does, because mild steel is a lot dirtier than stainless steel. Switch over to aluminum, whole different animal, whole different ball game.
In part 2, we break out the oxy fuel for some good old heating and bending. I'll take you step by step through the process as we pressurize the system, light and dial in a neutral flame, all the way to extinguishing the arc, depressurizing the system for proper storage. As always, thanks for watching, and until next time.
Keep your hood down. Don't stare at the bright lights.